Hello friends, this video is on partition function, which is a topic from statistical mechanics. In this video, we are going to discuss about how to write down the partition function and how using partition function, how can we calculate other thermodynamical variables. So we start with partition function. As we know that the probability of system is in a state alpha. The system is in state alpha is proportional to Boltzmann factor, which is proportional to Boltzmann factor, which is given by e to the power minus beta times EL, where EL is the energy of the system. Now, where beta is the shorthand notation for 1 over kBT. Now, the sum over all possible Boltzmann factor is called partition function, is known as partition function. Now, partition function is represented by symbol Z. So I write down partition function Z is sum over all possible states alpha e to the power beta L. Now, now using this partition function, we are able to calculate some thermodynamical variables such as entropy, enthalpy, and internal energy of the system and many. So, using this partition function, we are able to calculate thermodynamical variables. For example, internal energy, entropy, enthalpy, and etc. Now, our first topic is how can we write down the partition function for a given system. So, let's take a simple example, two-level system. So, two-level system. Now, what do we mean by two-level system? Means the system we have only have two possible energy values. Let's say minus delta by 2 plus delta by 2. And gap between this delta. Now, so for this kind of system, we can simply write down the partition function as z equals to e to the power beta minus delta by 2 plus to the power minus beta minus delta by 2, which is to the power minus beta delta by 2 e to the power beta into delta by 2. And we can write this as 2 times cos hyperbolic beta delta by 2. This is simple. Now we take another example, say simple harmonic oscillator. Uh, from quantum mechanics, we know that energy of simple harmonic oscillator is discrete, and which is given by En equals to n plus half h cut omega, where h cut is Planck constant divided by 2 pi, and omega is the angular frequency. Now, n equals to 0 corresponds to ground state. N equals to 1 first excited state. N equals to 2 is second excited state. So we draw the energy level. Let's say this is n equals to 0, n equals to 1, n equals to 2, n equals to 3. For n equals to 0, energy would be h plus omega by 2. For n equals to 1, 3 h plus omega by 2, 5 h plus omega by 2, and we have 7 h plus omega by 2. Now, for simple harmonic oscillator, we can write down the partition function is z is summation over n e to the power minus beta en, where summation over n is e to the power minus beta. We are substituting the value of en, which is n plus h cut omega. So we can write down as, we can take out e to the power minus beta h cut omega by 2 and summation over n e to the power minus beta h cut omega times n. So now what can we do? We open the summation. So we can, when we open the summation, what we get we get infinite series. Now one thing here, n goes from 0 to infinite. Look into the series. The series is GP series, where the common ratio is 1. Now the series inside this bracket is GP series, where the first term is 1, and this is infinite GP series, and which can be, and common ratio between the two consecutive terms e to the power minus beta which cut omega. So at the end of the video, I put the formula of infinite GP series. We will check it. So what we have now, we have to the power beta h cut omega by 2 divided by 1 minus the power minus beta h cut omega. Simple harmonic oscillator or partition function is to the power minus beta square omega by 2 divided by 1 minus 2 minus beta h cut omega. Now, our next step is to find out how this partition function is related to other thermodynamical variables. Let's start with internal energy. That's how partition function is related to internal energy. So the topic is relation between thermodynamical variable and the partition function. So relation between thermodynamical variable and partition function. First is internal energy. Now, the internal energy of the system denoted by U. So, and which is given by U equals to summation over E alpha to the power beta times E alpha by summation over alpha e to the power minus beta. Now, let's say this is the question. Now, see, the denominator is simply partition function. Now, if we divide the denominator with respect to beta, means del by del beta of e to the power alpha, what we get? We get this numerator for alpha e alpha to the power minus 1 minus 2. So, means del over del beta of z is equals to minus of alpha. We can write this. So, putting this in equation 1, putting this in equation 1, so we get u equals to minus del z by del beta times 1 by z. Now we can write this as minus del over ln z by del beta. So we got the relation between internal energy U and the partition function, which is del ln z by del beta. Sure. Now we know that beta equals to 1 over kbt, where kb is the Boltzmann constant. Now what is del beta then? Del beta is minus 1 over kbt square times del t, and we can write down internal energy as derivative of temperature as U equals to kbt square del ln z by del t. So this is another formula which will be useful. Now the relation between entropy and the partition function. Now we know that that now we know that entropy can be written in terms of probability in the form given by S S equals to minus KB summation over I Pi times ln Pi. Now this is one of the important formula for entropy. Now and for a system, now the probability for a system is in state I is given by Pi equals to the power minus beta Ei divided by partition function. Now taking natural log both sides. Now take the natural log both sides, which is ln Pi equals to ln the power minus beta Ei by z. So which is ln to the power beta Ei minus ln z. Or we can write as ln Ei equals to minus beta Ei minus ln z. Now put this in equation 4. Okay, yes. S is to minus kb minus s equals to minus kb summation over I Pi times minus beta Ei minus ln z. Now which gives us kb uh, kb times beta Pi ui plus ln z summation over Pi. Now this is nothing but kb beta times u plus this term is ln z because summation over Ei is equals to 1. So or we can write s equals to u by t plus ln z. So equation 5 is important range. Now there is a mistake here. It will be kb. Now the next relation is the relation between Helmholtz energy and the partition function. So now Helmholtz frequency is given by F, which is equals to U internal energy minus Ps. Now from equation 5, we have the minus Kb ln z is equals to ut minus f. So we can write as dbt ln z equals to u minus f, which is ln z by beta equals to f. So this is another important relation and easy to prove, minus ln z by beta. Now the next relation, which is relation number 4, is between heat capacity at constant value and the partition function. Uh, Heat capacity at constant volume is given by del U by del T heat. And, and we know U equals to kb T square delta ln Z by del T. So we have kb equals to ut del ln Z by del T time plus T square del square ln Z by dt square. So, so heat capacity at constant volume given by kBT to ln Z by del T plus T dt square of ln Z. So this is equation number, this is 7 and this is 8. The next relation is between pressure and Z. Let's we know that now thermal energy is given as F equals to U minus Ts. So Ts equals, so dF equals to du minus T ds f Td, and du is no, du is given by T ds minus T dv minus T dv minus of this two term cancel with minus P dv plus Td. Now at constant temperature we have P equals to minus del F del V constant, and so we can write P as minus kVT del ln Z by del V at constant temperature. So this is another important relation. Similarly, we can derive for disagreement. Now in second part of the video, we'll do some question We do for two-level system, we calculate all this quantity for two-level system and simple harmonic oscillator. Then we study the graph of heat capacity, entropy. So for today we stop here.